So we are going to do this problem from the 2015 Johns Hopkins Math Tournament in Calculus. Consider the real value differential equation u double prime of x equals u squared of x minus u to the fifth of x. Suppose that u prime of 0 equals 7 and u of 0 equals 2. Compute the largest value of the absolute value of u prime of x. Now the first thing to notice in this differential equation is it's not one that we're going to be able to solve. We can't use any of the methods we're used to, like Laplace transforms or variation of parameters or whatever, because we have u squared and u to the fifth in our differential equation, and that's going to make things really crazy to try to figure out. So we want to find a solution implicitly just in terms of u prime. Now if we want to find u prime, notice we already have a u double prime of x on the left side here. It would be really nice if we could just integrate. If we integrated u double prime, that would give us u prime. And then we would be able to figure out what is the biggest value that u prime can be. However, right now we can't really integrate this equation. And the reason for that is we have a u squared minus u to the fifth. And we can't integrate u squared because we don't know what u is. So there's no way to do that integral. What would be really nice is if we could integrate this in terms of u, because we know the integral of u to the fifth with respect to u is just going to be u to the sixth over 6, nice and easy. Is there any way that we could do that? Well, let's think about what we have right now. If we wanted to take the integral on both sides, we'd have the integral of u double prime of x dx equals the integral of u squared of x minus u to the fifth of x dx. And let's say we want to integrate with respect to u. And if it makes you happy, you can think about this as just substituting u equals u of x. Of course, that's not going to do very much. But what we have to think about is right now we're integrating with respect to x. If we wanted to integrate with respect to u, we would have to figure out du. Well, du is going to be u prime of x dx. So if we just had a u prime sitting right here, it would be so much easier. We could just do this substitution and then find the integral nice and easy. So can we put a u prime there? Well, pretty much we can. Because we have this differential equation, all we need to do is multiply by u prime on both sides. So if we do that, we're going to have the same thing on the left side of this equation over here. And then on the right side, we can put our u prime of x. Now that we have our u prime here, we can do our integral on the right side. But before we do that, let's take a look at the left side. We have a u prime and a u double prime. So this is actually a very nice case for a substitution. We're already using the letter u, so we'll let v equal u prime of x. And therefore dv is going to be u double prime of x dx. And we see why this is so good, because we have our dv sitting here. So now let's figure out both of these integrals at the same time. On the left side, we have our v on the inside of our integral times dv, and that's going to equal, on the other side, we have a u squared minus u to the fifth, and then u prime of x dx is going to be du. We can do both of these. So on the left side, the integral of v with respect to v is 1/2 v squared. V is u prime. So we get 1/2 u prime squared, and that equals 1/3 u cubed minus 1/6 u to the sixth. Then we just have to add our arbitrary constant c. So at this point, we're really close to being able to figure out the maximum value of u prime. The one thing that we're missing is the value of this constant c. And that's the reason that the people who wrote this problem gave us an extra condition. Whenever we have an extra condition given to us in a problem that we don't feel like we're really using yet, that's a good sign that it's going to help us out right where we get stuck. So here, u prime of 0 equals 7, and u of 0 equals 2. That means we're able to plug that into everything that we have here, and then solve for the value of c. That will let us figure out our final solution. So let's try that out. If we have u prime of 0 equals 7, then on the left here we have 7 squared over 2. That's going to be 49 over 2 equals 1/3 times u cubed is 2 cubed, which is 8. So we have 8/3 minus 1/6 times 2 to the 6th is going to be 2, 4, 8, 16, 32, 64. So we're going to have 64 over 6 plus c. And this isn't an algebra class, so I'll skip through all of the fraction manipulation and reducing stuff and give us the answer for c as 65 over 2. So that is the value for our c. We can go back to this equation we have here and plug it right in. So now we have an expression for u prime just in terms of u. And therefore we can just figure out what is the maximum value of that function that we have on the right. So I've cleared the board a little bit, and now we can try to figure out what is the maximum value of our equation on the right. Before we start working on that, I'm just going to multiply everything in this equation by 2, so we have u prime squared all by itself. That'll get us that u prime squared is equal to 2/3 u to the third minus, and then we have 2 over 6 is just 1/3 u to the sixth plus 65. So we just need to maximize 2/3 u cubed minus 1/3 u to the sixth, since of course 65 is always just going to be a 65. Now we can actually try to maximize this using calculus, and that will give us the right answer, but I'm going to try a little clever trick instead just to have some fun. If we take a look at what we have here, 2/3 u cubed minus 1/3 u to the sixth. Notice we have a 1/3 in everything, so we can factor that out. And then if we take a look at this, there's a u cubed in both of these terms. So what we actually have is u cubed times 2 right here minus u to the sixth over u cubed is just a u cubed. So if we expand this out, we'll get what we have right here. The reason this is significant is that this is actually an equation entirely in terms of u cubed. So if we wanted to substitute some other variable, say w equals u cubed, then that would mean what we have here is 1/3 of w times 2 minus w. And our goal is to maximize this. Well, we can just take a little graph and figure out what we have here. If we have w on the horizontal axis, and then w times 2 minus w right here, we're going to have a 0 at w equals 0 and a 0 at w equals 2, with our parabola pointing down just like that. The maximum value is going to happen when w equals 1. That means u cubed equals 1. And if we're just looking at real values, the only solution to u cubed equals 1 is u equals 1. And so without any calculus at all, we figured out that u value that gives us the maximum answer for our u prime. All we have to do now is plug it in to the equation that we have here, u equals 1. If we do that, we can basically just ignore the u's that we have on the right side. So we're going to have u prime squared equals 2/3 times 1 minus 1/3 times 1 plus 65. And if we want to find the biggest value of the magnitude of u prime, that's just going to be the square root of both sides. So the magnitude of u prime over here is the square root of 65 plus 1/3, just simplifying that inside a little bit. That is the solution to our problem. So the way that we got here is by looking at this differential equation and starting to think about minor changes to the way the problem is set up that would make our life a lot easier. For example, if we could integrate with respect to u. Then we start thinking, can we make those things happen in the context of the problem? We were able to do it in this case, and therefore we got to this equation that we were able to solve and get our answer just like this.